The next topic we're going to talk about here is what's called collision theory. And to make a chemical reaction possible, you have to have the reactants essentially slam into each other, and they have to slam into each other with the right energy and the right orientation. So collision theory is just the study of this to see what kind of energy the reactants need and also the orientation the molecules might need to have happen. Now, in a normal chemical reaction at about room temperature, they claim there's about 10 to the ninth or a billion collisions per second. And that's a lot of collisions. Whoa. But anyway, when you have 10 to the 23rd of these little atoms and molecules running around, it's not a big deal then to have that many collisions. However, it is still kind of fascinating. So the rate of the reaction, the speed of the reaction, will be proportional to the number of collisions. And activation energy, which gets the symbol E sub A, that's the minimum energy needed to form a product between a collision between reactants. So if you don't have that activation energy in the way the molecules come together, you're not going to have any products form. They're just going to the reactants will kind of look at each other but not do anything. So once you get to the activation energy, then you have enough energy for the molecules to slam into each other and actually make products.
For two molecules to react, they must collide. If an ozone molecule and a nitrogen monoxide molecule meet without enough energy to overcome their bond energies, a reaction does not occur, and the molecules separate without reacting.
So in this example, the molecules do collide, but they don't have enough kinetic energy to actually make the bond form. The N and the O there that hit each other, they're just like, oh yeah, sorry about that, didn't mean to slam into you. It's like a low collision car wreck, if you will. Not a lot of damage, maybe a tiny bit to the bumper or something like that. So this is an example of when the molecules don't have enough energy to actually make products. They have to have enough activation energy if they're going to actually make any products occur.
If the two molecules collide with sufficient energy to overcome the activation barrier, but with an orientation that does not allow new bonds to form, no reaction takes place. The molecules will separate unreacted.
Many reactants have a specific orientation or geometry that has to happen to make the products form. In this problem, we're going to make nitrogen dioxide here, and the nitrogen must smash into one of the oxygens. So in this video, the oxygen on NO bumped into one of the oxygens on ozone, and the oxygens really don't have any interest in each other. It's the nitrogen that wants the other oxygen. So this has the incorrect geometry. It may have enough energy to smash in, but the atoms aren't oriented in a correct way to make the correct products.
If a collision occurs between the two molecules with sufficient energy and the proper orientation, then a reaction can take place to produce molecules of O2 and NO2.
So in this video, the reactant molecules had the right energy and they had the right orientation. So they had enough energy to actually make the bonds start to occur. They had the right geometry that the nitrogen bounced into one of the oxygens, and that's what enough to make the oxygen pull off from ozone O3 and make nitrogen dioxide with the nitrogen. So this is an example of a successful reaction, all right? It had enough activation energy to make it happen, and the geometry was correct. And you need both of them to make that happen. So sometimes scientists will create what's called a reaction energy diagram, and this is an example of a reaction between a compound called methyl isocyanide, and it's making methyl cyanide, and methyl isocyanide is on the left, and methyl cyanide is on the right down there. Carbon is the black atom, and nitrogen is the blue atom. So the isocyanide has a nitrogen between the carbons, while the cyanide compound has the nitrogen on the end. And there's a lot of information you can get from a reaction energy diagram. So first of all, it shows in this case then reactants here on the left-hand side, and it shows the products on the right-hand side. And let's just kind of look through this here a little bit because there's a lot of cool information. So first of all, notice that the y-axis is energy, and the reactants are starting at a higher energy than the products. So right away, you can figure out the energy required to make reactants go to products. And because products are lower than reactants, that means this reaction is exothermic. It's going to release energy because reactants are in a higher energy state than the products. So one thing we can glean from this right away is actually something related to thermodynamics. The energy is going to be released. It's exothermic. That's pretty cool. But there's another energy term here, and that's E sub A right there. And E sub A is the energy of activation, or activation energy, same thing. And notice it's a pretty high barrier that the reactants must go through in order to get to products. So those reactants are going to try so hard to get enough energy to get to the top of this energy state right here. That's called the activated complex, or the transition state. We'll talk about that more. Now, once they get to the top, then it's like going crazy. They can go downhill, no problem. But getting to that point can be pretty tough. So all reactants need to overcome an energy of activation barrier in order to become products. And that has a lot of cool uses for it, believe it or not. So anyway, but no reaction is going to be energy free. All right, you always have a little bit of energy of activation in order to make products. Otherwise, reactants would just spontaneously go to products, which would have some crazy kind of ideas. Now, along the way, you can see there's these different pictures, and these pictures show different states of the molecules as you go from reactants to products. And this is a pretty cool part about science too. I told you at the beginning of this lecture, we're going to see what happens in the arrow, what happens between the reactants and the products. Well, these little pictures here are showing what's happening between the arrow, because in the old pre-chapter 17 days, we would have said this molecule here on the left goes to this molecule here on the right with an arrow in between. But now you can see what's happening. Those bonds are shifting around. You've got this weird thing at the top here where the carbon is actually connected to the pi bonds and the triple bonds, which is like science fiction to me. Anyway, it allows the cyanide to rotate around so the carbon can then connect to the carbon, and then finally you get down to the pathway at that final product, which is pretty cool. So this is literally showing what's happening in the arrow, how you go from reactants to products. It's a pretty cool thing. This is called a mechanism, and we'll talk more about this here coming up. These reaction energy diagrams are great. It shows you right away if it's exo or endothermic. So on the right hand side here, what we have in our little diagram is the lower graph. It's exothermic. The final energy, the product energy, is lower than the reactant energy. That means it's going to be exothermic. Your delta H value will be negative because negative things are exothermic. All right. You can, though, have endothermic reactions, the top one, where the final products are higher than the reactants. That means energy needs to be put in order to make that happen. That's a positive delta H. That's an endothermic reaction. But that's important. Anytime you can talk about thermodynamic stuff with chemists, it's a pretty cool thing. At the top of that little bump there, where at the top of the energy of activation, that little thing up there is called the activated complex. And you'll see some really weird chemistry when you get to the activated complex. So in this example, you can see that carbon is connected to the triple bond, the pi bond, and that makes no sense in terms of any stable molecule whatsoever. At the activated complex, you'll see things like carbons with 5 bonds, and you'll see carbons connected to pi bonds and lots of weird kind of orientations of things. So the activated complex is very unstable. It'll transfer over to the product or the reactant, depending on the energy, pretty readily, but it is kind of fun to think about as a scientist. That energy of activation, that energy gap between the reactants and the products is important. It's called the activation energy barrier, and all reactants going to products must pay this energy cost to make the transition possible. And again, without that, reactants would just spontaneously turn into products. I snap my fingers there to kind of give it extra dramatic effect. But anyway, you see the idea. Energy of activation is just a small barrier to keep reactants from going to products. And once you overcome that, then you'll have products, no problem. Some energies of activation are huge, some are very small. You can probably imagine that's going to affect the speed of the reaction, which is what this whole chapter is about. So hang tight, we'll talk about that more in a little bit. This energy of activation barrier is important. It literally is like amount of energy needed for reactants to go to products. We have a person on a bicycle who needs to get over the hill to get to the other side. And if you've ever bicycled before, it takes energy to go up a hill. Going down, though, is fun. Just whee, Anyway, I'm not a big bicyclist, but I do appreciate it. Anyway, the energy of activation is literally that way. So sometimes you'll have small bumps that are easy to get over. Sometimes you'll have big hills, big bumps that are harder to get over. And if you have a big hill, it takes longer to get to the top than if you have a small hill. So guess what? Differences in activation energy are the reason reactions vary from fast to slow. Small energy of activation, easy to get over. Big energy of activation takes a lot longer to get over. It takes more time. So when a chemist says why a reaction is fast or slow, it's due to the height of the energy of activation barrier. Now, some people on a bicycle come in full speed and it's easy for them to get over almost anything. Some people like me are more amateurs and it would take more energy. So it does depend on the initial reactant's energy, but regardless, big hills harder to get over for all people, small hills easier, stuff like that. You have to have those collisions with enough energy and the right geometry to make it happen. So you want, like that person getting over the high jump thing there, in order to get to the other side. Now, these reactions we've seen so far, again, are all showing as exothermic, where the final state is lower than the initial state. But you could have endothermic as well, which is really cool. Temperature absolutely affects rate. All right, and now we can begin to kind of understand what's happening. Now, first of all, let's just rewind a little bit. Rate constants K are temperature dependent. So when you calculate K at one temperature, it will be a different value at different temperatures. And now we can maybe begin to understand why this is the case. Because the energy of activation barrier is going to be the same hill regardless. But if you have a higher temperature, then you'll have more molecules able to get to the top, no problem. So the hotter the temperature, the more molecules can get over that energy of activation and become products, all right? So this is where it's cool. So there's a relationship between the rate constants K and the energy of activation, and we'll talk about this here in a little bit. But let's look at these two reactions. It's the iodine clock reaction. Both of them have iodide going to iodine. Iodine has kind of a purple color, while the iodine is colorless. And you can see the top one is basically room temperature and the bottom one is on ice.
A solution containing hydrogen peroxide is added to one containing iodide ion and ascorbic acid. This is a clock reaction, where after a small initial fraction of the hydrogen peroxide has reacted, a color change occurs. The same reaction can be performed at low temperature. Under these conditions, the color change occurs after a longer period of time.
So the top reaction, which was room temperature, took about 54 seconds to complete. All right, you can see the colorless color went to kind of this purple color. On the other hand, the bottom reaction, which was in ice, a colder temperature, took longer. It took 1 minute and 31 seconds. So generally speaking, you increase the temperature, you make the reaction go faster. It affects the rate. A scientist named Arrhenius came up with this expression, which is now called the Arrhenius equation. And this is kind of a weird equation as written, but what it refers to is it talks about the rate constant K having a dependence on E sub A, the energy of activation. So if you wish to calculate the activation energy for a reaction, you can absolutely do it. So the rate constant K equals something called the frequency factor, which we'll talk about later. You can think about the frequency factor as how many collisions have the correct geometry to make it happen. Anyway, then there's the Euler's number E. It's raised to the minus E sub A, where E sub A is the activation energy, and you divide by RT. Now, R here is the gas constant, the energy gas constant, 8.3145 joules per mole Kelvin, and T, of course, is the Kelvin temperature. So it's kind of a cool thing. When you're using using the energy R, make sure that you always use 8.3145. All right, don't use any other value for R. You'll find other ones out there, but you use 8.3145 for me in this class. Anyway, this is a cool equation because it is a way to calculate the energy of activation, the E sub A value, from a rate constant, which is cool. But what people usually do is they take the natural log of that expression. The natural log of Arrhenius equation, you end up with natural log of K on the left, natural log of A, and then natural log of E to the minus EA over RT. You can just get rid of the E part for that. So you end up with minus EA over R times 1 over T plus natural log of A. And you're like, oh, that's really helpful, Dr. Esel. Really cool. Okay, well, here's the idea. Just like what we saw earlier with the integrated first order rate law, when you can plot natural log of the concentration versus time to get a straight order, if you plot natural log of the rate constants K versus 1 over the Kelvin temperature, you will also get a straight line. And the slope equals minus EA over R. Now, R is just 8.3145, a constant. So if you multiply the slope by minus 8.3145, you will get the energy of activation. And this is considered the best way to find the energy of activation for a reaction. Now, the y-intercept equals natural log of the frequency factor. So if you want to find the value of A, you can anti-natural log e to the x, the y-intercept to find the value of A, which is kind of cool. But E sub A here is super cool for chemists. That little A thing, that frequency factor, has different interpretations, and that's kind of beyond where we need to be right now in this class. However, because some of you, I'm sure, are just dying to know, here's what I consider to be the best interpretation of the frequency factor. And so what they've done here is they've broken the frequency factor down into lots of things. There's something called the entropy of activation, which we're not going to talk about at all in this whole first year class. We will talk about entropy in Chem 223. But this is a way to find the entropy of activation, which is where they feel the frequency factor really kicks in. K sub B is the Boltzmann constant. That's the energy R constant, but per atom. So if you take 8.3145 and divide by Avogadro's number, that's the value you get there. You don't need to know that value. T is the Kelvin temperature. H is Planck's constant. We saw that in Chem 221. We'll see Planck's constant again in the future. Planck's constant, 6.626 times 10 to the minus 34 joule seconds. I talked about the entropy of activation, and the R factor once again pops in. We'll be seeing delta S again, definitely. Chem 223, we're going to hit entropy big time. Entropy is pretty cool, but for right now, just realize there is a use for the A. In Chem 222, I might ask you to calculate the value of A, but we won't be interpreting it in terms of entropy of activation or anything like that. A question that chemists will ask themselves is, how do the reactants go to products at the molecular level? Like, how did they figure out when the methyl isocyanide turned into methyl cyanide? How did they figure out that the carbon was connected to the pi bond? What we want to do in this section is we want to connect the rate law to the mechanism. We wish to connect the experiment, which is where the rate law pops in, to the theory, like how the mechanism pops in. And to do that, we need to know the reaction mechanism. And a reaction mechanism is just a sequence of events that describes how the reactants go to products. This is a theoretical field, all right? Like, you are basically thinking about it and trying to figure out, based on your data, how the reactants go to products. And there will be lots and lots of interpretations. So I'm showing here this picture of the ski areas at a place in Vermont. And let's say that we wanted to know how to go from the top of the mountain down here to the bottom of the mountain. Well, of course, you could just go straight from the top down to the bottom, which is totally fine. But maybe you'd like to take a more mellow method, and maybe you want to go like here, and then you kind of wander over this way, and oh, well, that's too steep, so I'm going to go this way and down that way. All right, so both of those paths, plus a whole bunch of different ones, are pathways you could take to go from reactants to products. So when we talk about in chemistry, reactants going to products, there'll be lots of ways to write this. And the more evidence you have to support your mechanism, the better, all right? So you'll be able to create some really creative mechanisms, but hopefully there's some kind of experimental evidence to support your idea. Like it'll support the best way to go down the mountain, something like that. So this mechanism we're going to create for a given reaction is just a sequence of events, how reactants go to products. Sometimes the reactions will go to products in a single step all at once, but a lot of times you'll have a series of what are called elementary steps to show how reactants go to products. So we're going to talk about this, the single step versus multiple elementary steps, as we go through this section.
When a fluoride ion approaches a methyl chloride molecule, a bond begins to form between the fluoride and the carbon. The molecule's carbon-chlorine bond lengthens and becomes weaker. The energy of the system increases. As the carbon-fluoride bond forms and the carbon-chlorine breaks, a configuration of maximum energy is reached, called the transition state. As the reaction proceeds to completion, the energy of the system decreases.
This is a very well-studied organic chemistry reaction where you have a carbon that initially has a chlorine. The fluorine comes in, pushes the chlorine out, and you end up with a carbon-fluorine bond while the chloride's by itself. This is considered to be a single-step mechanism. And what that means is all the reactants come together with the right geometry. They do their business in one particular step, and at the end, you're left with the product. So in this type of reaction, a single step mechanism, we would only have like one step right there, one hump in our diagram. And so in this diagram, we have a single hump. That's because it's a single step, all right? We can also tell from this reaction that it's exothermic. Products are lower than reactants, so delta H will be negative. And another term that we'll talk about more in a little bit, this is considered a bimolecular reaction. And bimolecular means that two chemical species are coming together to make the products. You can also have unimolecular and termolecular. We'll talk about that here in a little bit. Unimolecular, bimolecular, and termolecular are terms that are used to describe these elementary steps. And what we just saw in the last example is an example of what's called a bimolecular reaction. Two different molecules have to collide. Now, in the last example, we had a fluoride with the carbon species with chlorine. Those were our different molecules. But in reality, you could have two of the same molecules coming together and colliding. They have to be two separate molecules, but they can have the same identity. All right, just depends on the mechanism. A unimolecular means that only one reactant is involved. So like a bigger molecule is breaking down to smaller molecules. Termolecular is not as common, but if you do have them, it means that three molecules are coming together. So the little table there in the upper right-hand corner, unimolecular is just one piece breaking down to lots of pieces. In the first bimolecular, two of the same molecule, like two A's are coming together. But in the second bimolecular, you have an A and a B. The second bimolecular is what we had on the last slide. We had fluoride, that would be A, and the B would be the carbon with the chlorine species, so two different species. Notice though on the right side, the far right, the effect on the rate law. If you have just one species, then rate equals K times A. That's a first order process. We'll come back to this here in a little bit. If you have the first bimolecular one, the second one down there where A plus A makes products, then rate equals K times A to the second power. But if you have, like in the third one, the second bimolecular example, A and B making products, then rate equals K times A times B. So this might start to bring up some ideas here about the different things that are happening. Most reactions do occur in a single elementary step, but many reactions do have a sequence of elementary steps. And as an example of this, I want to show this mechanism here for how ozone decomposes. Two ozone O3 molecules break down into three oxygen molecules, and they feel this is a two-step mechanism. And if you look at those two steps, the first step is unimolecular. The ozone is breaking down to O2 and an oxygen atom. The second step is bimolecular. You've got another ozone reacting with the very reactive oxygen by itself to make two oxygens. Now, if you add the two elementary steps together, you can see that the oxygen gas, the oxygen atom by itself, cancels out, because in the first one you had oxygen as a gas as a product. The second one you had oxygen gas as a reactant. The oxygen gas will cancel when you add them up. The overall reaction, two ozones making three oxygens.
Gaseous ozone decomposes in two steps. First, one oxygen atom splits off. Next, the single oxygen atom reacts with a second ozone molecule to produce two molecules of O2. The product of the overall reaction is three O2 molecules.
If you have more than one elementary step, you will see more than one hump on your reaction diagram. So on the right-hand side there, you can see how reactants R are on the left and products P on the right. And there's two humps, all right? There's a big hump that you start with and a smaller hump right there. Each of those humps refers to one of the steps in this mechanism. So the first step, ozone breaking down to oxygen and oxygen, that's actually a pretty high energy step. It's hard to make ozone break down by itself. So it's got a big energy of activation, which is what that double-headed arrow is. Now, the second step also has an energy of activation, but it's much smaller. It's a smaller hill to overcome, so it's not usually a big deal. Once you've overcome the first big hill, the second hill is no big deal. So if you have more than one step in a mechanism, you're going to have more than one hump in your reaction diagram. And it doesn't always have to be this way, but often it's the first step, which is the highest energy. The reactants have to overcome the most energy to go over that hump, then the subsequent hump or humps are smaller.
Hydrazine is formed in aqueous solution in a three-step process, each step being bimolecular. First, a molecule of ammonia reacts with a hypochlorite ion to form chloramine and a hydroxide ion. Next, the chloramine reacts with a second molecule of ammonia to form a charged species with a nitrogen-nitrogen bond. Finally, the charged species reacts with a hydroxide ion to form hydrazine and water.
You should never add home cleaners that have ammonia to bleach. All right, just don't do it. There are so many bad reactions for your health that can happen. It's not even funny. This is one example of what can happen. And again, there's more than one reaction that can occur. But when you add ammonia, NH3, and this is in things like Windex and stuff like that. But anyway, ammonia and hypochlorite, OCl-, which is the active ingredient in bleach, they do all kinds of nasty things. And so in this reaction, we're looking at how they make hydrazine, N2H4. And hydrazine is a rocket fuel. You can probably imagine you don't want that in your house. So again, just don't mix bleach with household cleaners. It's not a good thing. But anyway, neither here nor there. This reaction is considered to be a three-step mechanism. So three steps mean there's going to be three humps. One first one, two second one, three third ones, all right? Each of them has their own energy barrier, but you can see that the first one is the biggest, the one that has the double-sided arrow. So that's going to be the biggest energy of activation in this reaction. And in that, ammonia reacts with hypochlorite to make a compound called chloramine, NH2Cl, which is super nasty, and some hydroxide, all right? So that's bimolecular, two pieces are coming together. Now, the second step has that chloramine, which is really reactive. It reacts with another ammonia to make what's called protonated hydrazine, N2H5+, and chloride, all right? And that's lower energy of activation barrier. The chloramine wants to react really fast. And also that protonated hydrazine in step 3 reacts quickly with hydroxide to make regular hydrazine and water. So overall then, you can see the reaction is two ammonias and hypochlorite, making N2H4 plus water plus chloride. So 3 steps, 3 humps, 2 steps in the mechanism, 2 humps. If it's a single step, only a single hump. You get the idea. All reactions have what's considered to be a rate determining step, an RDS. And the important part here is that the whole mechanism won't be any faster than your slowest step. And they say sometimes that a chain is no stronger than the weakest link. Well, a reaction is no faster than the RDS, the rate determining step, the slowest step. All right. So what we can do here is look at an example of how this kind of works out. Let's look at the reaction of iodide, I-, reacting with hydrogen peroxide, H2O2, which is HOOH here. It reacts with some acid, H+, and it makes iodine, I2N2 water. And from the experiment, we're seeing here how rate equals K times iodide times H2O2. Now notice that iodide and H2O2, they're both first order. It doesn't state the little 1 power up there, but that's what that means, all right? So iodide and H2O are both first order. Earlier, I stated how the stoichiometric coefficients are often different than the orders of the reaction. And boy, do I want to highlight that here, because for iodide, there's a 2, and you can see that iodide is a first order reactant, so the 2 and the 1 are certainly different. Now H2O2 has an invisible 1 in front of it, and H2O2 is a first order reactant, so that one's the same. But also notice how H plus has a 2 in front of it, and H plus doesn't even show up in the rate law. We're going to see that things that don't show up in the rate law are 0 order reactants. So what that means here is H plus has a 0 by it. It's a 0 order reactant, which is totally crazy. So anyway, we'll see how this mechanism and the rate determining step can help us make sense of what's going on with the rate law. Also note in the pictures in the lower left, we have 2 blue barriers, all right? And you can think about those blue barriers as like energies of activation. In the first picture on the left, notice how all the cars are kind of jammed up there by the first barrier, all right? That's going to be the bigger energy of activation. It's harder for the cars to get through Plaza A, all right? It's a slower reaction. But on the second picture right there, there's more cars jammed up at Plaza B. So Plaza B has the higher energy of activation. So this rate determining step is like which one they can get through faster. In the first picture, it's Plaza A, which would be the rate determining step because the cars aren't getting through the plaza. They get through B okay, it looks like, but the A is slow. On the second picture, it's Plaza B, which is the rate determining step because it's preventing the cars from getting through to number 3 right there. If that helps, cool. Sometimes people help this visual, but anyway, if it doesn't, just ignore it. A scientist has proposed the following mechanism for how iodide reacts with H2O2. And you can see that this is a 3-step mechanism. So if we drew out a reaction diagram, it would have 3 humps to it. And you can see in the first step, hydrogen peroxide reacts with iodide. It makes hypoiodous acid, HOI, and hydroxide. But also notice that this mechanism has slow, fast, and fast. It claims that step 1 is slow, and we'll talk about the meaning of that here in a little bit. Now, the second step is apparently fast. Hypoiodous acid, HOI, is a very unstable acid. It reacts with iodide to make iodine and hydroxide. And finally, the third step is also fast. This is just hydroxide and acid making water. And that's going to happen really good, very exothermic, etc., etc. If you combine all of those steps together, you'll see that you'll get the overall reaction right there. So a good mechanism, if you combine all the steps, will give you the overall reaction. Notice that the slow step has a relationship to the reactants in the rate law. We talked about how iodide and H2O2 are both first order. If you use one iodide and one HOOH in your slow step, they will both appear in the slow step. H plus did not appear in the slow step. H plus is not really something that affects the rate. H plus is a 0 order reactant. Lots of cool information here, but let's kind of go back over this a little bit. So first of all 3 steps, when you add them together, should give you the overall mechanism, and that's what happens. But more importantly here, the slow step is what chemists are after. The slow step is the rate determining step. It's going to determine how fast the reaction goes. And any reactants in the slow step will be part of the rate law. So in the slow step, there's one HOOH and one I minus. And in the rate law, rate equals K times iodide to the first power, HOOH to the first power. That's where these orders of reactant are coming from. It's the slow step that determines what chemicals appear in the rate law. In this problem, nitrogen dioxide and carbon monoxide are coming together to make nitrogen monoxide and CO2. And this scientist has proposed this two-step mechanism. Step 1 is slow, step 2 is fast. If this is a valid mechanism, which of the following rate laws would apply? Okay? And the punchline here is that in order to answer that, you want to focus on the slow step, because any reactants in the slow step will appear in the rate law. So notice that for the first answer, rate equals K times NO2 to CO, if that was a valid rate law, the slow step would have one NO2 reacting with one CO, and that's not what we see for the slow step. The second answer, rate equals K times NO2 to the first power, that would be NO2 as the only reactant of the slow step. That's not what we see either. But the third one, answer C there, rate equals K times NO2 squared, that would imply that in the slow step, two NO2s are coming together to make subsequent pieces. So for this particular reaction, if this is a valid mechanism, it had better be answer C, because the slow step in the proposed mechanism has two NO2s coming together. NO2 reacting with NO2 means it's a second order reactant. So the rate determining step, which is nothing more than the slow step in a mechanism, super important to chemists. And any reactants in the slow step should appear in your rate law, which is kind of cool. So back to this mechanism, 3 steps, 3 humps. So in the picture in the upper right there, there's 3 little humps right there. Notice that the first hump is the biggest energy. When you start to end, it's the biggest amount. Biggest energy of activation would be the slow step, all right? All of these steps essentially are bimolecular. They have 2 molecules coming together. Even step 3 can be considered it, because one OH reacts with one H plus to make one water, even though there's 2, but anyway, it's a silly thing. But anyway, if this is a valid mechanism, the slow step will be proportional to iodide and H2OH, which is what we found in the lab, and that's what we see. All right, that little A thing is proportional to, it's an alpha symbol, so the speed is proportional to the iodide and H2O2 to the first power, and that's what we see in the rate law, so that's why that's legit. HOI and OH minus are called reaction intermediates. And intermediates are things that appear and then disappear. So if you look to the mechanism, HOI appears at the end of step 1, and then it's used up at the beginning of step 2. So it's a product in step 1 and a reactant in step 2. So when you add them together to give the overall reaction, which is right there, there's no HOI. HOI is a reaction intermediate. And the same thing for hydroxide. Now in this case, there are 2 hydroxides created, but they're both used up in the last step to make water. So reaction intermediates appear and then disappear. So if you're a scientist and you're proposing this mechanism and someone says, oh, I don't think you have any, you're not a good scientist, you don't know what you're talking about. Well, maybe you could detect HOI in the solution, and there are systems with lasers and stuff that allow you to do this. So finding a reaction intermediate can prop your proposed mechanism in the light of other scientists. So it's kind of a cool thing. You could do the same thing, and might be easier to look for hydroxide, by the way. There is a reaction mechanisms handout which goes over this material in more detail. You might want to check it out to get a better understanding as to what's going on. In this problem, we've got a compound called methyl iodide, CH3I, and the chloride is essentially pushing the iodide out to make a methyl chloride, CH3Cl, and iodide is then released. Well, we have two groups of scientists that are competing for the mechanism. In the first mechanism by the first group, you can see that the methyl iodide is essentially decomposing in a unimolecular step to CH3 plus and I minus. And then in the second step, CH3 plus chloride makes the CH3Cl. And notice that the first step is the slow step. Now, the second group of scientists thinks mechanism 2 is better, and they're proposing that methyl iodide and chloride make a wild kind of 5-coordinate carbon species that has all the hydrogen, iodide, and chloride. That's a slow step. And then in the second step, the iodide is ejected to make the expected products. Well, you come in trying to decide which one of these is better, and if you do some work in the lab, you find that the rate for this reaction equals K, the rate constant, times methyl iodide to the first power. And the question is, which one is the better mechanism based on your rate law? Well, if you found that methyl iodide was a first order reactant and you didn't find any evidence that chloride was affecting the rate, i.e. chloride was a zero order reaction, then you want a reaction where only CH3I is present in the slow step, no other chemicals. Because if there was chloride, then it would appear as a chloride to the first power or something like that. Mechanism 1 is literally that. It's methyl iodide breaking down to other products. So your rate law is consistent with mechanism 1. All right, chloride is a zero order reactant. It doesn't affect the speed. Methyl iodide, though, does affect the speed. It's first order, and that's what mechanism 1 is saying. If you would have found that the rate law equals K times CH3I times chloride to the first power, you would have picked mechanism 2 because their slow step had two chemicals in it. So you'd expect to have both CH3I and Cl minus in the rate law. But that's not what you found, so mechanism 1 looks to be a better mechanism here. Mechanisms are really helpful. Organic chemistry uses mechanisms a lot to predict what the products are going to be. And I'm just going to show you two examples here of what are called SN1 and SN2 mechanisms. SN stands for substitution nucleophilic. You'll learn more about this in organic chemistry, but they can be super helpful.
In the unimolecular SN1 mechanism for a nucleophilic substitution reaction, the bond between the carbon and the leaving group breaks prior to formation of the bond between the carbon and the entering group. In the bimolecular SN2 mechanism for a nucleophilic substitution reaction, the formation of the bond between the carbon atom and the entering species occurs simultaneously with dissociation of the bond between the carbon and leaving group.
So you can see how the SN1 was essentially a two-step mechanism, had two different parts in it, while SN2 was a single step. So understanding how these mechanisms work can be super helpful in organic chemistry. You'll spend some time learning about SN1 and SN2 there, definitely. A catalyst is just a chemical that can make the speed of the reaction faster. And a catalyst is pretty cool because it's not used up itself. So if you put one molecule of a catalyst in, it can have lots and lots of transformations go through it before it's actually used up itself. So we rely on catalysts a lot. Our bodies use lots of catalysts to make a lot of the things happen for life. In biology, anything with an ASE ending is basically a type of a catalyst. But that's for biology, not for me, that's for sure. But anyway, catalysts can be really cool. So in the pictures there in the lower part there, you have an example of a catalyzed pathway and an uncatalyzed pathway. In the uncatalyzed pathway, reactants go to products. It's exothermic in this example, but it's a single step, and you can see how the energy of activation is pretty high. So what a catalyst does, which is in picture A, it lowers the energy of activation barrier down. So it's lower barriers is like a lower hill that you have to go over on a bicycle. It's easier to do. It'll be easier for reactants to go to products. Now, catalysts work by somehow injecting themselves into the chemicals and then re-emerging unscathed at the end. So what that means for us is that catalyzed pathways have to have at least two humps, at least two steps in the mechanism in order for reactants to go to products. Without the catalyst, it's easy to go reactants to products by itself. But with a catalyst, you'll have at least 2 steps in order to transform those reactants to products. So it provides an alternate reaction pathway. It's the same overall exothermic, endothermic kind of considerations, but you do have a lower energy of activation, which makes it faster.
In a platinum-based catalytic converter, nitrogen monoxide molecules in the exhaust stick to the surface of the platinum. The molecule decomposes, each atom remaining on the surface. When another NO molecule comes to the area, it also decomposes, and its N atom bonds with the other N atom on the platinum surface. The O atoms also combine. The gaseous nitrogen and oxygen molecules then float away from the surface. A significant source of air pollution in many cities is the emission of nitrogen oxides by gasoline engines. The problem is not as severe as it was a few decades ago, due largely to the advent of devices called catalytic converters installed in automobile exhaust systems.
A catalytic converter is a great example of how a catalyst has helped our society a lot. And in the early 70s in Los Angeles, places like that, smog was a real problem. And it was mostly due to exhaust from cars. It would react with the water, make it very hazy and stuff. And it wasn't good to breathe, jazz like that too. Well, the introduction of a catalytic converter to a car allows some of those smog-creating chemicals like carbon monoxide and nitrogen monoxide to be created into other chemicals. So carbon monoxide is usually turned into carbon dioxide, while nitrogen monoxide is turned into nitrogen and oxygen. And those chemicals, at the very least, aren't as bad for humans. Carbon dioxide certainly is greenhouse gases, so I'm not saying we're totally scot-free, but at least it doesn't create the smog effect that we see, and it's healthier. Auto exhaust systems with catalytic converters often use an expensive transition metal. Platinum, palladium, sometimes nickel are used. Sometimes you hear about people ripping off catalytic converters from cars because the metals inside are worth a lot of money, unfortunately. However, the big picture, they make us all a lot healthier, and I personally don't think they should do that, but who am I? I don't know anything. Anyway. Other uses of catalysts include making all the plastics that we use. Polymers are essentially plastic. We'll talk more about that in Chem 223. You can take ethene, which is CH2, it's got a double bond, and turn it into polyethylene, which is used for lots and lots and lots of different kind of substances. Making acetic acid, vinegar, from methanol, CH3OH, is actually a good use of a catalyst. And again, like I said, all of our bodies use catalysts all the time. Enzymes are biological catalysts, and without them, we wouldn't be able to do a lot of things that we take for granted as human beings. This is a picture from 2025. It shows turning an alcohol into an aldehyde. Now, the alcohol would be like methanol there, CH3OH, and it's turning it into an aldehyde, which is a carbon hydrogen with a double bond on it. It's pretty cool. This is a brand new thing. It uses some kind of molybdenum catalyst. A lot of times the identity of the catalyst is kind of a trade secret. They don't usually reveal that, which is fine. I just think it's kind of cool that they are starting to get movies of this kind of transformation.
Hydrogen peroxide in water decomposes slowly at room temperature. In the presence of manganese dioxide, however, the decomposition occurs much more rapidly. The reaction produces oxygen and water. The manganese dioxide is not consumed or otherwise altered by the reaction. It serves only as a catalyst and makes the reaction occur more rapidly.
We've talked about the decomposition of hydrogen peroxide into water and oxygen, and hydrogen peroxide will decompose eventually to water and oxygen. It's true. However, if you add a catalyst, as you can see, it goes a lot quicker. Manganese 4 oxide, i.e. manganese dioxide, is one example of a catalyst that makes this happen. But now that we understand the diagrams, we can create a picture like the one there in the lower right. So the black line represents the uncatalyzed reaction of hydrogen peroxide added to water and oxygen. It has a higher energy of activation, so it will happen, but it's a bigger hill to overcome. And so it's harder for the reactants to get the right amount of energy to overcome it and become products. If you add MnO2, however, it catalyzes the reaction. So it lowers the energy of activation considerably. It's a lot easier for the hydrogen peroxide to break down. And like all catalysts, then, you have two humps. The first hump will be for how the MnO2 injects itself into this system. And the second hump there will be how the MnO2 somehow gets itself away from the system and is recreated at the end. So in the video, that kind of brown water there, if you'd evaporate off the water, you'd have MnO2 left over. You could reuse the MnO2, make it break down some more hydrogen peroxide. Catalysts are pretty exciting. This is a picture of taking a compound called cis-2-butene and turning it into trans-2-butene. The cis-C4H8 is being turned into trans-C4H8. Now, if you look at the overall reactants to products, products are a little bit lower. This is an exothermic reaction, so it will happen. But if you don't add a catalyst, that black line shows you much higher energy of activation. It's a much slower reaction having the cis go to the trans. If you add, though, iodine, I2, it tends to catalyze this reaction, and it makes it have a much lower energy of activation. So those red bumps up there show the different steps. In this case, the slow step is in the middle, and this is something you can figure out too. We're not going to talk about it, but the middle step is the slower one. The important part here is that if you want the cis to go to trans, add a catalyst. It makes the reaction a lot easier to happen. That barrier is lowered quite a bit. It's easier for the reactants to go to products, and you are good to go. Okay, so that's it for Chapter 17. I appreciate you spending your time with me here. I hope this has been useful. If you'd like some more practice with any of the Chapter 17 material, definitely check out the resources that are listed right there. Also remember that I'm here to help. You can talk to the Learning Success Center / Avid Center located above the library on the Mount Hood Community College campus. They are there to help you. Using their resources is free for you as an MHCC student, so it's no big deal. Thank you for spending your time with me. Again, I hope this has been helpful. Have a great day.